We have quantum computing webinar, and we have session after session every Friday, and we are going to look at the book. So my personal journey is that I tried for the test and failed, but that is very normal with me. I usually fail the test the first time. In fact, I have to take it, fail it, and then I'm going to do it right. So that is the book we're looking at, and I'll tell you more about this book. These are the slides that are coming from this book, and the lab, I'll give you the lab. All right, with all of that, first of all, let's start about learning. If you click here, then you will see the book. That's the book, that's a familiar cover, and perhaps you have seen that book, but okay, Michael is interested in this technology to allow learning computational capabilities for healthcare image. That's very interesting. So, Michael, will be very interesting if you come up with something, either existing or something that you come up with that will be great. So tell us what we learn. But back to that book. That is a very interesting book. Even if I mentioned it, it's worth mentioning it again. The book was published the first time in 2000, in the year 2000. 10 years later, they celebrated the 10th edition, and they have now a preface and a summary at the end, but not much change. They're amazing guys, Mike and Ike. They're called Michael Nielsen and Isaac Chuang, are working researchers and working teachers, and whoever you talk to who is in the area, they will tell you they are the best. Now, I bought a paper copy too, because it is somehow different from reading online. So at least you can put a bookmark. So I'm going slowly, and that's what I'm going to offer you today. Now, here's the chat. I would like to see quantum processor CPU be designed. So that is also an interesting thing. By the way, you can find out that Intel is also having a quantum computing initiative, and their approach is somewhat different. They want to combine the regular CPU with the quantum CPU. So as soon as I know a bit more in detail, I'm there, I'm in the network, I'm signed up to get the stuff. So I'm there exactly, but I was working on the test. So now is the time to go back. So the time is to go back to this book. So what I prepared for you is this. First of all, the truth is you can find that book as a PDF. That may be the intent or may not be the intent, but you can find it, you can Google and you can find it. So I don't think I did too much of a bad thing if I uploaded it to my folder. This is the webinar folder. So if you click here, you will get our webinar right here. And the book is right here. Book is Nielsen. That folder is open. So if you just go there you are. That is the book. Now, there are other versions of this same book. There are summaries, there are a few pages, but there is also the whole book. That's what I wanted to show you. And another thing that I wanted to show you is that I keep updating the slides. So I have a few slides for you to see. Let's click on that. And they will show right here, but I think I also have prepared them for you on the desktop, probably here. No, I have not. Let's go back. I will put it on the desktop like that, and I will open that. And to begin the conversation, let's look at some of those slides. That will be a good start. Now, just checking on the chat. that's a very interesting conversation guys are having, and I'm glad we are having this book. This conversation, because that's a meeting of people who are interested. So these are my slides that I use in class, and you know what? The slides are right here, so I'm not going through all of them. But if you open that run file, open that file that I gave you, and if you click on the folder, you'll get them. You'll get them, so I'm showing you what I want to show, but I'm not worrying, you can get them if you want. So this is a video, and we are not doing that video right now. This is a book for babies, quantum computing for babies, and showing that you have, in fact, you have not seen it, so you can buy it to your favorite baby. And that link is somebody reading this book out loud with the pictures on YouTube. So if you're interested in that, you can do this. But I'm interested in the next few slides, which summarize what Mike and Ike have said as a global perspective before they start quantum computing with the first bit or with the first qubit. They give you those interesting facts, which is amazing thing. Again, if you look at the book, you will see that Peter Shor, one of the inventors of the algorithms and one of the, so to say, founding fathers in that sense, and a working researcher who is alive and well at his university, he says that they have combined the exact facts in the best possible way. In other words, that's not only a bestseller, that is the Bible, that is the, however you call it, the best book on that. And it's amazing that it stayed on this top seller list for 20 years. All right, so that's what they do. They introduce you to quantum computing as a discipline, and next step is let's play with that one bit. So as they say, you combine the four different areas. You combine quantum mechanics, which is the physics, and then you combine computer science, which is computer science, but that's not enough. You also need information theory, and you also need cryptography, and all of that we will touch upon. And since you guys are chatting, I'm once in a while checking that. So the history, when did it all start? Well, it all started around in the 20s and the 30s, 1920 and 1930, when the classical physics wasn't cutting it. It was based on a simplistic worldview. It was thinking that atom is just like the solar system, and the sun over there is just like the nucleus of the atom. And if you think this way, you will come into all kinds of contradictions. You will see physical impossibilities, and things are not like that. In other words, they saw pretty fast laws are different. And they saw that, yes, there is a quantum mechanics applicable to these particles, and these particles are not behaving in the normal expected way, right? That the intuition, our intuition based on big things is not cutting it. And they had to change the rules. So they changed the rules, they had quantum mechanics rules. One of these strange rules was that you cannot copy an object. Well, I have to go much deeper in this, but you cannot duplicate an object. Now, in our regular world, duplicating a bit is nothing easy, and in fact, we do it non-stop. We copy information from one place to another. Well, it turns out that in quantum mechanics, you cannot. And there were a few other things that you would expect that logic or common sense should tell you it should be doable, and it's not. One of them is that you can connect two particles in a special way, and they will keep that connection so that whatever happens to one happens to the other, even if they're separated by a long distance. Now, that's not logical, because that means that one particle transmits what happens to it to the other particle, and it's doing it much faster than the speed of light, and that nobody wants to believe. These are just two examples of quantum mechanics. So after all, after that, I would say that a major part of history became people coming to grips with these rules. Once you accept that your logic, your common sense logic, your macro object logic, it doesn't work there, then you're okay. So much of the history is just accept the world as it is. And Richard Feynman, he likes to formulate things very well. So he said, guys, here's the universe. And if you don't like it, well, sorry, find another universe for yourself. Because that universe, which is our universe, it has all these unusual rules. But if you accept that and you get the quantum mechanics as a new law, then you see that it works. It works for so many things. One of the things that people often quote is our GPS. We use GPS everywhere and all the time, and it's based on quantum mechanics. More precisely, it's based on a very precise clock. But other things also are possible with this quantum mechanics, the structure of the atom and nuclear fusion and so on. So I'm not reading what it says, but what is it? So here you have also a couple ways to approach that. And most mathematicians prefer to just say that it's all mathematical rules. That's one way. Not everybody loves math, but some people do. If so, you can say that what we're dealing with are vectors and forget about quantum mechanics and the physical world. We just deal with vectors, and every quantum bit or qubit is in fact a vector. Then we can apply some transformation to it, and transformation are described by matrices. So from here on, they have went away from physical essence, from the physical reality, whatever it is, and into math. I have a friend with whom I accidentally started talking. He teaches at um, Chicago College, and he sent me an article which is mostly about mathematics of quantum mechanics. And he says, when I teach this course, I go away from physics as quickly as I possibly can, and then I'm in the familiar world of math, vectors, and matrices, and I'm fine. So that's where it is, mathematical framework. Well, Mike and I do it mostly like this, but they don't insist on it, so it's very readable because they don't have fear of quantum mechanics, and they are not forced to go straight into math right away and forget about physics. So, but there is also a physical theory behind that. So once in a while you feel that, yes, I need to know that too. I need to know what is behind. Well, we'll show that. And these are simple rules, but they're counterintuitive. That's the major point. Counterintuitive, and here are some of the counterintuitions. No cloning. It's illogical, but you cannot clone a quantum object. However, that opens another possibility. If you cannot clone, what can you do? You can send sort of this object to another place. It will be the same object. The first one disappears, but the next one appears, and that's teleportation. So yes, you have quantum teleportation. Quite amazing. That's why we're all here. And that all started in 70s and 80s. And what they wanted is control over individual quants, individual qubits, or individual methods. Because we are all, here we are, right? We're big, too big. But we want to take advantage of the qubits of individual bits, individual atom, individual photon, electron. Well, that's called controlling single quantum systems, and it is possible. It became possible in the 70s and 80s. And again, the last time I will express my amazement that the book did this. It built a complete system, even though they didn't have the physical reality back then. But then now they do. And whatever it said back then is true today. Now, let's see, people are talking a little bit. You know what? We'll look at this chat. So we chat away, but we'll look at that later. So if I say that you are able mm, to imitate the qubits based on the elementary particles, then I need to be able to control them. That indeed happened. That was number one. And the second thing happened is the quantum computer as an idea. Now that you can control individual atoms, individual photons, individual electrons, then how about building it into a cohesive computer system? Is that possible? So let's see who suggested that. Uh, we'll come to that a little bit later, who suggested that. But what they suggest is that if you can control individual electrons and if you can force them to do this dance for you, then perhaps they can do the computation. Since our bits are only 0 or 1, but our electrons, photons, or whatever represents a qubit, they can be 0 or 1 or a distribution of those 0 or 1s in between. Then they can do much more work. One qubit can look through all of the possibilities, and therefore you can theoretically compute much faster. So let's look at what does it mean, much faster. For that, we need to look at efficiency. You can have what's called efficient algorithms and not efficient algorithms. And we all understand what it means, but we want to formalize it a little bit more. So we will say that efficient algorithm is polynomial in size. That let's say I'm asking you to find uh, sorting order in n objects. So how will that sorting algorithm work as a function of n? If it works as n squared, that's bearable. N to the third, that's bearable. If it is 2 to the power of n, that's not bearable. Because n to the third is reasonable in size, and you can build a computer that will solve the problem. But 2 to the power of n is not reasonable in size. When you have, let's calculate, you only have 10 to the power of 90 particles in the whole universe. So once you get into these numbers, then you cannot solve it with the classical computer. And that's called not an efficient algorithm. Yes, what you give me is an algorithm, but not a computer algorithm because you cannot really practically use it. Now, when do you get to this? Well, 2 to the power of 3 is 8, so that's approximately 10, and therefore you get to the 10 to the power of 80 or 90 when you have 2 to the power of 93. So once you have 93 objects, you're out of your resources. Okay, and that's called Turing machine. Turing machine is an abstraction that says just advance one position and go back one position. And that abstraction allows you to imitate or think of all our existing algorithms. And if you can prove that Turing machine cannot do this, well, you have proven that you cannot do it. Unless, of course, unless you have other ways to go. One possible ways to go is an analog computer. because analog computer could do a lot of things at once. You can imagine that it works on, let's say, light maybe, or a physical uh, something, that it can solve multiple problems. For example, you imitate the real system that you're trying to do, and instead of calculate using Turing machine and an algorithm, you use an analog computer. So analog seems to be the miracle speed up of the standard computation, but it's not. The reason it's not is because these are big things, so they wear and tear. The knife is not sharp anymore, and the measurements are not precise, which is translated into the word noise. So if you have an analog computer, then theoretically it can solve problems much faster, but practically it is too noisy. That doesn't work. The lesson was that you had the chance, but you blew it. Let's put it this way. Okay, and then let's do this. Let's use analog computer, but for analogs, let's do the particles. Let's do photons and electrons. And now we're coming to more or less today. The first researcher who started this is David Deutsch, alive and well, and I think, again, Massachusetts, Chicago University, right? And he invented the first algorithm. So he went through these ideas that you define a computational device and use the particles for your computational elements. And if you can only deal with noise, then you might have a computer. All right. So as we know, David Deutsch created an algorithm, but another algorithm was created by Peter Shor. We're almost today, 1994. That's not too long ago. So he invented an algorithm that works on quantum computers and that can work at the same time on all the possibilities. So as I show in another slide, the rule of quantum computing is this. You give it the problem, you go away, you don't watch, and when you come back, the problem is solved. That, of course, is a good children's book, the real story that you set it with an algorithm. The algorithm includes Fourier transform, if your electrons can do that, and that creates a much smaller space than you need to explore, but you're working on the whole space all at once. So Peter was the first, Peter Shor, who invented this algorithm, and today it has been practically implemented. His algorithm can factor the numbers. So it can take a very big number and it can factor into prime dividers, right? The only problem is that today they have only solved it for number 15. And 15 turned out to be 3 times 5. And that is great, but we need big, big numbers, but they're not too far away. That is the story. Me personally, it took a long time to believe that we're talking about uh, this newly developed area where there are no breakthroughs as yet. Everybody's waiting for them almost every day. That do or we already have the algorithm that will beat the classical computers? And in theory, yes, we do, but in practice, no, we don't quite. These are the names that are there. And the first person here was Richard Feynman. So he said that, you know, we have another problem that he wants to solve. It's not the computational problems. He doesn't care much about computational problems, but it is the quantum mechanical problems. He says you can describe, you can write out all the formulas, but you cannot solve them on a classical computer. So what if we do this? What if we let electrons imitate themselves? And maybe that will become a quantum imitation computer that will finally give us the results. And we will be calculating the quantum mechanics on a quantum mechanics computer. That's 92 idea. that became true. Today we have IBM that gives us computers remotely, and the largest one is 433 bits, qubits, which is still not enough to practically use it and break all encryption in the world, but it's getting there. That is very exciting for many people. So from here on, I'm using my older slides, and I'm explaining how I'm going to take one bit and how I can use not a bit but an electron to represent this bit. An electron can be zero, meaning it's looking up, spinning up, or it may be one, meaning that it's looking down, or it can be anything in between. That's the power of a qubit. So it has an infinite number of states, not only 0 and 1, but everything in between. Well, okay, that is how it works. So you select the qubits, and then, as I mentioned, you go away and you don't watch. That picture shows the girl who is not watching, closing her eyes. Well, that's what you should do. Okay, so well, we'll talk about later. And to make it more palatable, look at the waves that represent the light. So if that photon, which is particle or which is the smallest portion of light, if it is really a particle, then it goes either through that hole or through that hole, with the result that you have either this black shadow or this black shadow where it doesn't hit the hole. But in practical life, we all know that that shows interference, and it's not a particle, it's a wave. And the end result is that, yes, it is a wave when you watch it. It's not a wave when you don't watch it. And the end result, how can it be? Good question. So that just explains how this electron can have all the states at once. And therefore, that becomes our basic unit of calculation. It's called quantum bit, and it can be anything in between, just like this picture shows. Well, so far, now I'm going to skip that. We already mentioned a few things about this. So far, what we did is an introduction to quantum computing, something that provokes some questions which we might pick up at the end. But now practically, what do we do? In other words, every session here has some theory, interesting talk, but it also has some lab that we should do. So let's do that. Let's try to do the lab. Now, usually I give you a link, and I will give you the link, but I'll change something this time. Here's the quantum computing lab that I'm giving you. So I'm giving you that. I'm putting it here. Okay. But usually I say this. You can take this from the link. Here's the link. You can go to the very first lab right here. I call it introduction because we are going to play with that one qubit. We are really going to do it. And you can download that. In other words, if you want to do it, you can download the raw file, click here, and it will download. And since I'm on the Mac, I can go to the download folder here, download folder, and here it is. Then you need to run it somewhere. It's a Python notebook. And usually I tell you guys, go to Colab. Colab is an environment, free environment from Google, where you can run your labs like this. You say File, Upload, and choose the file. And it's right here because I just downloaded that. And it will show you the complete lab. Okay, so that really is a full complete lab. But I'm not going this time today, I'm not going to run it inside of Colab. That's because Colab is a very nice environment. You can run it, but I think it's time for us to become a bit more real. And the problem with this is that you start running it. So you say right here, you run it, and it says, but you don't have Qiskit Lab. You don't have Qiskit package. So you would have to install it. Usually I tell you, please install it. But today I'm going to do something else. I think that if you really are serious about running, then you need to prepare your environment. Exactly how you prepare your environment, that's described here. Since I gave you the whole lab, I gave you the setup. And in this setup, it says that is how you install all of that. So today I'm not going to go through that is how you install all of that, but instead I will run exactly in my environment, local environment, where everything is installed. And that way I will not have to repeat my install every time. You know, it's very nice, very easy to say, oh, just import it like this. Here's a line, you say pip, you start with exclamation point and say pip, install, and that's Python installer, and it will even help you. You say Qiskit, and it says, yeah, I know Qiskit, and it will install it. I'm showing you. So it's installing. But now we're forced to install for the pleasure of doing it real quick. We're forced to install it every time I go to another lab, same thing. And then I also have to install that. So instead, what I do, what I usually do in my work, I first of all install Python and Jupyter, and then I run that. Let me show you how I do it. We go to the project, we go to Quantum Lab, we pull whatever latest changes there were, if there were any. Okay, we have to say git reset minus minus hard, and that means drop whatever changes there were, but please pull whatever changes there are, and that way you'll get the latest, greatest. And then you do Jupyter Lab with a Y, Jupyter Lab. Okay. If you do this, you will see all the labs in the browser, like this. And the lab I'm interested in is back to the basics, the very first. But again, if you really want to do it, I recommend that from here on, you don't use Colab because that forces you to redo it every time. But instead, you run it like this in your local environment and don't depend on anyone. Let's verify one thing. I had to activate. I have to say conda activate Qiskit. In other words, I have to package whatever I need for that. I have to package under a virtual environment. And again, that you can read if you don't know those virtual environments. You can read about this right here. That's the lab that I gave you, and it tells you how to do it. So I did it. I assume that I did it. That is the theme. It is on localhost. Now I'm running locally, and I can. Why does it do that? Oh, because now I need to restart Jupyter. Okay, so I hope I didn't confuse you too much, but it's all there. In other words, It's all here in this lab, GitHub lab, and it's open. It's for you to clone, and I'm closing all the rest and open that one that I want to show you today. So all this theory about one bit and one electron, how does all that work? That is one way to look at things. But another way to look at things is, what do I do as a programmer? And that's here. Whatever we spoke about, that's implemented by IBM in their library called Qiskit library. And that's probably the most popular library. So if I were you, I would start with this one, and we're going to run it in a minute. Now, this is Python notebook, and if you're not familiar with that, then it is like Harry Potter newspaper. It's alive. It gives you the explanations, and these explanations, you can all edit them by double click. So I double click here, and that is the markdown format that I use for the explanations. After that, I run it, and it becomes normal. This is code, so that's alive. You can run this code in the browser. That's what we're going to do. Now, is IBM the only one? No. There are quite a few different libraries. Google has their own. Intel has their own. And first, we need to learn from one. So that's what I'm suggesting, that we all learn from Qiskit, but everything will become very easy later. And we will be able to just compare. And that's how it looks in Google. That's how it looks in Intel and any other. Okay, so that's where we are right now. Well, let's run. Let's see what we are supposed to do to deal with this magic. And what we're saying is that step by step, I'll show you how to do it. First of all, we import the necessary packages. The first package is quantum circuit. So we're going to build ourselves a little quantum computer right there. And how big, that we will decide right here. Here we're saying build me a quantum computer that will have 2 qubits and 2 regular bits. That's what that means. So number one, I will do kernel and restart and clear all output so that you will see that it's real and not pre-recorded. Okay, all is clean. I come here, and there are 2 ways to run a cell inside of Python notebook. One is click right here, run, and it shows a star all the time that it hasn't finished, and then it shows the number of the step after it's done. So it was able to import those packages because I previously installed them right here. Okay, now it can deal with them. Another way to run it is hold shift, and then do return. And that will do it again. And you see it changes the number 2. If I do it again, I shift, return, number 3, we're done. Okay, now the explanation is that we're going to build ourselves a computer of 2 qubits. What's the max? Well, 433, but that will cost about, so in real life, what you do in real life is that you build as big a computer as you want. You cannot go more than 433, but you probably will not go there anyway. That is because at that size, the computing time costs $2 per second. So maybe $2 per second is not the first thing what you do. Instead, your first thing will be a simulation. All right, everybody understands the advantages of simulation because it's free. So we build the computer. Let's go there. We build ourselves a computer. And by the way, those guys who are already, guys and girls, who already have done similar things, it's a repetition. Yes, you know that. But it's a journey that we're starting all over again, and we're starting from square one. We will go to the next square next time. All right. So far what we have done, and maybe I'll make it a little bit bigger. Yeah. that is a little bit bigger. We're going to add something to that computer. So what we're going to do is there are two qubits, and I can act on qubit number 1 and qubit number 2. What can I do with them is called transformations. Transformations in terms of computer science, or really in terms of computer science hardware, are called gates, using the old term for that. So this is the Adamar gate, this is the control not gate, and then the measure. The Adamar gate takes my qubit and makes it more real. It becomes now probabilistic. It can be either 0 or 1, and it has certain probabilities. So I took the qubit 0 and I applied the Adamar transformational Adamar gate to it. Then I took qubit number, again, that same qubit number 0, but now I'm saying make not this qubit. It was 0, it should become 1. If it was 1, it should become 0. And if it is in between, it should kind of become not in between. To say what it really means, not in between, you would need to spell it out, and that's next week. But for now, you apply the not and the control not. You control it by the settings of the next bit. The next qubit, if it is that's number 1, that's the second one. If it is 0, then we do not apply CX, and if it is 1, then we do apply CX. And then we want to measure. So that all is explained here, and the mark gates on qubit 0, a control not operation, which is explained here. And now we want to see what kind of computer we have built. Okay, let's run it here. It shows me that's what you've built. And now let us draw that. That is something you can impress your friends with. That's a real quantum computer with 2 quantum bits, qubits, with then a measure operation here on the first one and the measure operation on this one. And where do we measure? To the real bits, because initially when we started, we said 2 qubits right here and 2 real bits. Oh, well, these are also real, 2 classical bits, and measure them or copy the state onto 0, 1. These are classical bits, so they can be either 0, 1, they cannot be in between. Well, that is just a computer that I built, but I have not run it. How do I run it? For that, I need to bring in a here simulator, right? And for that, I need to first import this simulator like this. And there's air. These are the 4 basic metaphysical elements of the world: air, earth, fire. I think they are this, and that one is air. And then you build a simulator right here. And you are saying that simulator will imitate a real computer, a real quantum computer. So I'm taking a circuit that I just created. I'm compiling it for the simulator. That's called transpiling. And using this transpiler right here, I'm taking the circuits and giving it the emulator, and then I'm running it. Since that is a quantum computer, it could have noise, and therefore I'm running it much more than once. I'm running it 1,000 times. Shots is 1,000. But since it's a simulator, it will really come up with the same answer every time. Well, let's do that. That ran, it says it got the first quantum bit output as a 0 and the second as a 0. That happened 531 times, and 1 and 1 for the first and second qubit happened 469 times, and that's the real result. Now, if I run it again, like this, I get a different count. I only get 1 and 1 or 0, 0, but I get this a different number of times. Now, why these numbers? Because I take those first 2 qubits right here. This is the 2 qubits. What I do with them is I take the first one and make an Hadamard state, which has an equal probability of resulting in 0 or 1. So that's why you see about 500 over the 1,000. That's the first one. So it will stay at 0, 1. But then I'm saying, depending upon what the second one is, say a not to the first one. Well, the second one is 0. So say the not to the first one always is true. And the end result is that we get the first one, but not the first one. And that's true for the first and the second one. Then you can visualize the results. And that's even better. Well, that was the first exercise. For those of you who have done it a lot, the difference is that we do it locally. We set everything up, and I welcome you guys to email me during the week and tell me, well, something doesn't work for me, and I will help you. But what we wanted to accomplish today was this. We wanted to get some theory and then get some practice. And here you are. We accomplished all of that. So what I do now is stop sharing the screen and address your comments. And maybe you will get more comments because there are no pictures to look at. Okay, so we see explanations that you guys were giving. A good question, Mohammed. So how can qubit be both 0 and 1 at the same time? I think we should say that it's not really 0 or 1 at the same time, but it has the probability of being 0 or 1 after you measure that. So if you take a real bit, it doesn't have the probability of being 0 or 1. It's either 0 or 1. But the qubit, based on a particle, we understand that if we measure that, it's really a wave. I'm using this trick. I'm saying, but it's really a wave, even though it doesn't make sense. But it can be either 0 or 1 when you measure it. And that's what I showed you in the lab, that you get different results every time you run it. Okay. Yeah, please try this weekend. Colab is also great for learning. And this time, I recommend that you become serious and prepare your own environment, and I'll be very happy to help you with that. Now I see some maybe more questions. No, no more questions. All right, and congratulate everybody and myself on coming to the end. And I wish you a great week and a great year ahead, right? And please work on that. And I'll see you next week. Thank you.